I'm assuming that you've had some version of correlation and regression before. So can you confirm that for me very quick? Can you tell me whether or not you've seen correlation and regression before in your stats courses? Yeah, okay. Ooh. So I want to talk about it again here. Again, this is not meant to be super in depth, but just to sort of refresh our memories about it and how correlation is measured. Because when we start talking about the very next topic, which is like on Thursday, we'll talk about classical test theory and reliability. It's going to use a lot of the information that's underlying correlation regression, which is this idea of a covariance. Like, for instance, the Cronbach's alpha, which is a measure of internal consistency reliability we'll talk about on Thursday, is based on the covariance between items. So it seems odd to jump into talking about that unless we make, just to make sure that we talk about what that all means. Because we're used to talking about correlation, because correlation is this sort of fixed value that it has for measuring relationship. Where covariance, I think it gets sort of lost in the shuffle. So we're going to talk about, just a reminder, scatter plots, go through an example of sort of correlation, the correlation coefficient. Actually, this stuff, the other kinds of correlations, factors affecting correlation, tests for significance, I realized I took it out, but I didn't take it out of this. So we're actually not going to talk about the other kinds of correlation or factors affecting correlation. Originally, I had this in here, and I cut it out because it's not particularly relevant for what we're talking about the rest of the course. So I sort of decided to cut it to sort of get to other material like the item and test scoring and all that stuff sort of quicker, not sort of spend so much time on this. But so I'm not going to talk about those things, but let's talk about what we are going to talk about. So correlation really gets at this idea of, how do two variables relate? And a lot of times people just, they look at the numbers and, try to decide whether or not values are significantly correlated with one another or not. And it's a way of sort of deciding that. And, but just like any significance test, it depends a lot on not just the value of the test, but also the number of subjects and a bunch of other stuff too. So people get a little bit sort of lost when in that they sort of forget about those things and look solely at the significance level. So the question really comes down to, are two variables related? Like does one increase as the other increases? So for instance, you're going to the college and you're getting training to develop skills with the idea that those skills should correlate to higher income, more knowledge, more skills, more income. So there should be a positive relationship between the skills you have and the income that you make. Okay. You also get things like this one increases, the other decreases. Like, do health problems increase when your nutrition, or at least the quality of nutrition, sort of decreases? I have a feeling that it's very possible. I'm sure people are doing studies on this now, but think about sort of life now during the sort of pandemic. I think most people's eating habits and things have changed. For a lot of people, it's changed one drastic way or the other. You're either eating a lot more healthy now because as you're staying home, you're cooking more, able to decide sort of what it exactly is you're eating and not sort of eating out all the time. Or it's going the other way and you go into sort of simple, basic foods, like you're always just eating mac and cheese or peanut butter and jelly sandwiches or something like that because they're just easy. You're home, you don't feel like dealing with cooking a bunch of food. So there's probably going to be a lot of things looking at the correlation between people's nutrition and health problems that can be triggered by this, by the pandemic. That I'm sort of interested, I'm sure people are likely either studying or going to study. There's all kinds of COVID-19 related like grants and things out there, just looking at exactly how COVID has impacted things. And it's impacted things in every conceivable way, I would imagine. But anyway, so this is looking at typically we call like a direct or positive correlation, where this is looking at it's either called an inverse relationship or a negative correlation, right? Where two things are sort of going in opposite directions. One increases, the other decreases, and sort of vice versa. And then how can we actually numerically measure, like quantify the degree of that relationship between the variables? So that's typically what we want to do with correlation. So oftentimes it sort of starts off talking about sort of scatter diagrams and graphical depictions of things. Like here's, you know, a scattergram, a scatter plot of hours of playing video games per week and the number of alcoholic drinks someone consumes per week. I'm assuming maybe at the same time, drinking while they're playing video games. I don't know. This is not real data. It's sort of made up, but it seems true, seems real. I don't know. So the amount of times people are playing video games per week sort of correlates, or at least what you see as a general trend, right? So even without doing anything statistical with this, you can sort of see that there is a general trend of scores going this way, that as these numbers increase, these are also increasing, right? Same thing, as they decrease, they're also decreasing. So the general pattern like that, right? So this is why it's called a direct relationship or a positive relationship. Both things are going in the same direction. So they're directly related, meaning as one goes up, the other goes up, one goes down, the other goes down. They're directly related. This again becomes important again for things like Cronbach's alpha and other things when we're looking at the relationships. Depending on how items are worded, it's very important that all the items be sort of flipped to make sure they're all in the same direction and directly related, or else that can substantially impact the measure of things like Cronbach's alpha and liability. So there's another one, still like average hours of video games per week, and then up here you get sort of exam score. This is sort of the inverse relationship, that as these are going up, right, as you're going up in video games here, right, per week, the numbers here are going down. Right, so you're actually it's going this way, along with that way. So low numbers, low values for this correspond to higher values of this. So here you're getting this sort of pattern going down this way, which is sort of the inverse. So if the trend starts off sort of high on the left and goes low right, and that's a negative or inverse relationship. If it starts low left and goes high right, then that's sort of a more positive or direct relationship. Okay. So an example, and this is one I've used a bunch because it's interesting. Look at it. It's a little bit dated. I think it's like from 1988 or something like that. But the smoking cigarettes increase systolic blood pressure. Actually, not this. We're going to get back to smoking cigarettes in a second. But if you plot the number of cigarettes, so here's plotting the number of cigarettes smoked per day against systolic blood pressure. You know, you start to see this trend that the more smoking occurs, right, the blood pressure starts to increase. Now, this is of course impacted by this person up here that had a 160 systolic, and they smoked roughly 23 cigarettes per day or something like that. But you get this sort of general trend, and correlation just looks at the sort of general relationship. When we start getting at the trend, this actual line here, this prediction line, that's regression. But they're pretty much doing the same thing. One is just sort of putting a direction to the relationship. Regression is going, from X to Y, where correlation is really just looking at any relationship at all. But they're both versions or measures that are related to covariance, which we'll get to in a second. The relationship is moderate. Why do we care about relationships? So, what would you conclude if there were no relationship? If the line was flat, right? What would you conclude? Yeah, you started to say impact, but then you stopped, right? And it's interesting because it does, language-wise, it does become interesting because you can't, because even if with this line here, we can't say that smoking impacts blood pressure. It just predicts it. So we don't actually know if it's the smoking that's causing the rise in blood pressure because it's not experimental, it's just a prediction. So if the line were flat, though, we can at least say there was no prediction, that smoking doesn't seem to predict the systolic blood pressure if it were flat. And if it were negative, it was going the other way, right? If it was going this way instead, I mean that the more you smoke, that actually reduces your blood pressure or predicts a reduction in blood pressure, right? If it's near perfect, what does it mean to be near perfect? Yeah, if all these data points are actually all right on the line, like the line fell just exactly on the points, it would mean that there would be a sort of one-to-one correspondence. As you go, one additional cigarette per day, you go up a certain amount of blood pressure. It would be exact amount and like perfectly matched. There'd be very little error, very little residual. Because even with this line here, we're predicting that a person who smokes this amount here, right? We're predicting that they would, have about a 125, maybe, I'm just guessing. But you can see that someone actually here smokes about that amount, and we drastically underestimated. So there's this amount of data, right, that's in here, and this thing is called a sort of residual. It's like how off we are on our guess. So if we had a near perfect prediction, everything lined up right on the line, we'd have almost no residuals, no mistakes, no over or underestimations based on our prediction model. All right, so our model would like perfectly represent the data if it were perfect that way. All right, I mentioned that before. So here's the data I was talking about. This is like real data. It's 21 different countries, and they measure the amount of it's the average number of cigarettes smoked per adult per day in that country. And then you looked at the number of coronary heart disease deaths per 10,000 in the same country. So we're used to, seeing data that's at the individual person level. This is actually at the country level. So each one of these is a measure of a country's sort of response or average. And this is from like 1988. It's a little bit old, but the first country here that has the most cigarettes per person per day is the U.S. Right? We were the leading smokers in like 1988. Okay. And we see the coronary heart disease deaths. So here too, we can actually start looking at things like the relationship between cigarette consumption and CHD mortality. So CHD mortality goes on the ordinate plane, which is sort of the Y one, or cigarette consumption goes on the abscissa, which is the X one. So we can start, plotting things like this. This is the cigarette consumption, CHD mortality, and we can start to look at how these things relate. Each dot here represents a country. Right, so we had 21 countries. There are 21 dots on here, all representing each of the 21 countries and their consumption and CHD mortality. Back up again. And then the line is there just for clarity, but we'll come back and talk about that in a second. For now, we're just talking about the relationship between these things. And you can see that like this particular point here is a country that had 6 cigarettes per adult per day. And they had 11 deaths per 10,000. So whatever it is, country number 8, 6 cigarettes per person per day, 11 deaths per 10,000. So that represents country number 8 there, which I don't remember off the top of my head who that is, but at this point it doesn't matter either, I don't think. So what does the scatter plot show? Well, it definitely seems to be a trend. It's not a very neat trend. I mean, it's there. You see this sort of trend, but it's not like everything's sort of lining up perfectly on this line. There's a lot of variability, a lot of room for sort of errors and things. It looks pretty strong, but again, there are going to be residuals or sort of errors in prediction that we're not quite going to be able to capture with this data. So let's talk about correlation, the relationship between two variables. And correlation really comes from the term correlation. What is the correlation between two different things? I mentioned before, Pearson, like in our first day, that the Pearson product moment correlation is the most common sort of version of a correlation measure that we use. And he's considered one of the sort of founders of modern psychometrics. So types of correlation, positive correlation, again, high values in X tend to go with low, high values in Y. As X increases, Y increases. You got negative correlation, is the opposite. High values of X tend to be associated with low values of Y. As X increases, Y decreases. Then you get no correlation. So no correlation means that sometimes high X goes with high Y, but other times high X goes with low Y. There's like no pattern. So no correlation, a zero correlation really means there's really no consistent pattern of how X and Y relate to one another, which comes back as basically just being all over the place. So there's no consistent value. So the correlation coefficient is a measure of degree of relationship between 1 and -1, and the sign refers to direction. So if you're in the negative side, it's a negative correlation, positive side, positive correlation. And it's based on this thing called covariance. And this is a big part of why we're talking about this and rehashing this stuff you've seen probably before. Probably even in high school, you probably had correlation and regression. It's this idea that oftentimes when you're taught about correlation and regression, it skips over this idea of covariance altogether. You go straight to talking about correlation, calculating R, without talking about covariance, when really a correlation is just a standardized covariance. And covariance is a measure of sort of degree of variation or variance that's shared between two variables. So think of it as variance, but with two variables instead of one. You're probably going, what the hell does that mean? How do I get two variables into a variance? This is just again, the correlation. This is like a near perfect one correlation here. So how things are lined up exactly on going from low left to high right. This is a strong, it's like a one perfect correlation. Here, it's still going low left to high right, but you start to see that they don't line up perfectly on the line, but it's still, still a general pattern there. Here, there's no pattern. It looks just like a box. It's just all over the place, right? So this is where you get this zero correlation. There's no trend either from low left to high right or high left to low right. Then you get a sort of zero correlation. For negative, you're getting high left to low right. And if it's perfect or near one, they're going to line up very, very strongly along the line. And have a very distinct pattern like that. All right, so you all just did a homework assignment that had to do with looking at variance. So what's the and we just talked about it again, but let's make sure we're all on the same page. What's the equation for variance? Now there's like a sum in there. Yeah, so it's sum of squares over degrees of freedom. So that's xi minus x bar squared. Exactly. Okay. So we have this idea of we're taking each score minus the mean, and we're squaring it to get a squared deviation of each score around the mean. And then we're going to get what's essentially an average, but we're going to divide by degrees of freedom to give us a better estimate of the population. And that we typically call sum of squares over degrees of freedom. Everybody with me so far? That part's pretty easy, pretty standard, pretty straightforward. But I can easily rewrite this as the sum of xi minus x bar times xi minus x bar, right? That would be the same thing. Those are mathematically equivalent. Everybody see that? All right, Jessica's with me. What about everybody else? Okay, so those two things are the same, and it's assuming basically just for squaring the deviations. But what's to keep me, if I have two variables, x and y, what's to keep me from just changing one of these to y instead? If I do that, simply changing one of those values out of there, I've changed this from a variance to a covariance. And instead of thinking about it as sum of squares over degrees of freedom, this is now sum of products over degrees of freedom. It's the same basic idea. Just take, if I start with person number 1 in a data set, that means person number 1 has to have a score on x and a score on y. And basically say, take person number 1's score, subtract the mean on x, take the person number 1's score on y, subtract the mean on y, and then multiply them together. Create a product. Do that for person 2, do that for person 3, all the way down to person n, last person, and then sum up all of those products and divide by n minus 1. And that'll give me the covariance between x and y. With me so far? All right. So we're thinking about, we have two variables. We have x and y. And we got a bunch of people. 3. All right, all the way down to however many people you want. Right? N people. And so every person has to have a score. So this person has a score on, this is, person 1's score on x, person 1's score on y. All the way down. Person 2 score on x, 2 score on y. I keep writing it. X instead of y. And sent all the way down to, you have an x n and a y n. Right? So you have all these different responses to those things, right? So when looking at these different things, looking at any one person, when would a person in this list here contribute a positive value to the covariance? Let's think about the top for a second, to the sum of products up here. When would it contribute a positive value? So when the mean is less than an individual score, but on which one? All right, you're getting there, but let's go a little bit further in there. So one has, because you're saying one has to be higher than the other, but I just want to make sure what you're talking about. One what has to be higher than another what? Think. Well, okay, so if this is positive and this is negative, if I multiply them, I'm going to get a negative. Now you see, because I'm multiplying, whatever this is. Yeah, so this is being multiplied. It's a product. So this minus this times this minus that. That's what I'm saying. So when would a person's contribution be positive? For person 1, you do it for person 1, and then person 2, person 3, 4, 5, 6, 7, and sum across all the people. All right, so you essentially would have, for everybody, you'd have an xi minus x bar times yi minus y bar all the way down for every single person. Then you can sum them. Okay, so you got to be like, down here. Oh, yeah. Or our scores need to be higher than the means on both sides. Oops. So a way to say that is, if in order to get a positive value up here, anybody's got to contribute a positive value, both of their scores have to be on the same side of their means in order for it to be positive, right? So they both have to be above the mean or both below the mean. And then that would be this would be a positive contribution, right? If they're both above the mean or both below the mean, because if this was below the mean, it'd be negative. Below the mean is also negative. Negative times a negative is a positive. So I would get a positive contribution as long as they're both on the same side of the mean. With me so far? Are you sure? Ask questions now. Something's not clear. All right, so if this is the mean on x here, represented by this, right? This is the mean on y there. So as long as they're both on the same side, I'm going to get a positive contribution. Now, for most people, there's a tendency, a trend, for most people to be on the same side of the mean on both x and y. I'm going to get a positive covariance because I'm going to sum all those up and divide by n. I'm pretty much going to get an average that's going to be a positive number because there's a general trend of that. So what about the opposite? When would I get negative contributions? When would a person's sum of product up here, or person's product, be negative? Yep. One's above and the other is below, like that. All right. One here I have x is above x mean. Here y is below y mean. If that's true, this is above, positive. This is below, negative. Positive times negative, it's going to be a negative for that person. Same thing as the other way around. If this is below the mean, that's negative. This is above the mean, that's positive. Right? So if the values are on opposite sides of their means, they're likely to be a negative contribution to the covariance. At least their product's going to be negative. If there's a trend where most people tend to fall where one variable is above, the other variable is below, you're going to get an overall negative covariance. With me so far? So please ask a question. That's exactly right. But what I'm leading you towards is hopefully a better understanding of what not just covariance is, but even correlation. Because correlation is based on covariance. So let's try to understand of what is covariance generally trying to tell us. If the covariance is positive, what does that mean? As we said here, that means there is a general trend for scores on x and y to be on the same side of the mean. They're either both above or both below, right? If a covariance is negative, so it means that x and y are on the same side of, it's really each of their means. It's not like there's one mean, each of their means, right? If a covariance is negative, then x and y are generally, at least on average, on opposite sides positive covariance, high means or high scores on X tend to go with high scores on Y. Low scores on X tend to go with low scores on Y. All right? High scores on Y tend to go with high scores on X. Vice versa, low scores on Y, low scores on X. Make sense? So watch my hands for a second here. So with negative, high scores on X tend to go with low scores on Y. Low scores on X tend to go with high scores on Y. High scores on Y go with low scores on X. Low scores on Y go high scores on X. Right? So there's this opposite thing. If the covariance is positive, scores tend to go on the same side of the mean. They're not perfect, but they tend to be on the same side of the mean all the time, right? Whatever that is. When they are negative, they tend to go in opposite directions, like this instead. Okay, we're all right around the mean. This tells you that there's a general trend for which side of the mean the x's and y's tend to be on. If it's positive, they tend to be on the same sides of the mean. If it's negative, they tend to be on opposite sides of the mean. That definition of covariance is actually the exact same definition you have for correlation. A positive correlation means that x's and y's tend to be on the same side of the mean. For negative correlation, they tend to be on opposite sides of the mean. They tend to have an inverse relationship. So then what's the difference between a covariance and a correlation? It's sort of the same difference between raw scores and z-scores. So raw scores are not standardized, they're just in regular units, whereas z-scores are standardized. So if I want to take my covariance and make it into a correlation, how do we typically standardize things? How do we standardize scores? If I want to take a z-score, or sorry, regular raw score, turn it into a z-score, I do that by, all right, so I take take a score, z equals some score x minus what? How do I turn raw scores into z-scores? Right, so this part, the top part, this thing is just, I don't know why I'm telling you this, but this thing is actually called centering. Right, so by subtracting the mean, I'm centering the data at 0. So this part's not necessarily the standardizing part, it's the centering. It's the dividing by s. This is what standardizes it. It makes the movement of scores 1 unit. It's like going from saying 12 inches to 1 foot. Right? It's making the amount of change from one standard deviation to the next standard by dividing it by a standard deviation and making the movement of standard deviations now 1. So this process of dividing it is standardizing it. This up here on top is just centering it so that the mean is at 0. So if I want to standardize my covariance and turn it into a correlation, I have covariance of x and y. So a correlation really is just the covariance divided by the standard deviation of x times the standard deviation of y. It's just taking the covariance and standardizing it based on the 2 variables that went into it. So a correlation is just a standardized covariance, where covariance can be in any number. It could be in the hundreds of thousands, it can be tiny. Covariances depend on the scale that the variables are measured in. And they're often times kind of odd, because if I'm correlating, say, time with distance or something like that, then the covariance is going to be, the units are going to be like miles per hour. It's going to be a combination of time and distance. Correlations, because we divided by the standard deviations, it takes those metrics away. We no longer have to worry about what they originally measured in. It all becomes standardized. It now becomes between -1 and 1, right? We don't have to care about what the original units were in because we've sort of removed them by standardizing. So a correlation is just a standardized covariance. Covariance measures the degree of which people's responses are on the same side of the mean or on opposite side of the mean. And correlation is just doing the same thing, just standardizing it. So if you have a 0.7, positive 0.7 correlation, that means there's generally a trend for people to score on the same side of the mean on two variables. When you have, it was a negative 0.7, this tells you there's a general trend of people that answer on the opposite sides of the means of the two variables. It's just that we've standardized and removed the scale out of the variables and created this standard thing, just like a z-score. There's standard scores, so that no matter what what the variables are measured in, we can compare them because there's a standard scale to sort of be able to compare them across. So does that help you sort of get a deeper understanding of correlation and the relationship between variables, or do you have questions to what that means? Because I know I can actually be a little bit confusing because it might mess with your previous understanding of correlation, maybe? I don't know. Ask questions. Tell me what you're thinking. I mean, it's also like what is the conceptual idea behind what a correlation is? A lot of people throw correlation out there and be like, oh, they're related. Look, it's 0.7. But what is a 0.7 or what does the covariance between these things actually mean? What do we actually measure? Why do we care if a thing is positive or negative? What does it mean to be directly or inversely related? It really has to do with where they are relative to their means and how that actually sort of plays out. What's the average placement of scores or responses of people relative to the average people responding? Yeah, it can be anything. Yeah, so covariance is just like variance, right? It's in squared units. They're sort of confusing, like, what does a squared deviation mean? And then we add them up and we get this sort of, it's as a descriptive measure, it's really kind of difficult to understand. All right, so I have an average of 17 plus or minus the squared unit thing. It doesn't really help, right? And they can be in any value. The larger scale is if I'm measuring something like if these are high school GPA and college GPA, the covariance can be a tiny little number, right? Because it's all just 0 to 4. It can be a small number, but mean a very large relationship. If this is number of hours worked or something, and your salary, these numbers can be in the hundreds of thousands and represent a small relationship, right? Because it's all in whatever the scale they're measured at, on, like hour, salary per hour or something. I mean, it could be very large numbers that mean very little relationship, which is why we started to sort of use this measure to standardize them so we can understand whether or not the relationship between them are very large or small, because we now understand that this is the maximum positive, maximum negative, and this gives us a standard with which to compare all relationships so we know if they're sort of large or small. We can even test them. We can do significance testing with the correlations. But still comes down to, what's correlation really measuring? It's really measuring the degree to which people are on the same side of the mean or the opposite sides of the mean on two variables. Sure. Mm-hmm. Yeah, I mean that sounds about right. I'd have to look at the math a little closer, but yeah, I see what you mean. At least it feels like that's correct. I mean, like you're trying to find a common numeric value with which to sort of divide into the top part. A different way of thinking about it, I mean, if that helps you to understand that, that's perfectly fine. But there's another version of correlation that I'm not going to remember off the top of my head perfectly, I don't think, where it's the correlation equals, it's like the sum of the z-scores multiplied by each other, yi divided by n minus 1, I think, where we're not multiplying the z-scores. So here we're standardizing first, right? Each one being standardized first. So each one of these is having, you know, they're being divided by their s of x or s of y to standardize them. And then we're cross multiplying and then getting an average. So whether you sort of standardize first and then get an average, or sum all the products together and then standardize, you still get the same. It's the same process. All we're doing is figuring out a way to standardize the units out of each of the scores to get a standard measure of the relationship. And whether you sort of subtract and multiply first to get your covariance, because oftentimes this is what gets taught in a lot of textbooks. So that we just use z-scores or some other versions, and it sort of skips over the fact that covariance is sort of sitting right there, because we're going to come back and talk about covariance when it comes to things like Cronbach's alpha, looking at classical test theory, that the degree to which covariances sort of play a factor in there is important. And when most textbooks and most stats courses sort of just speed on by any mention of sort of covariance at all, because we don't typically use covariances a lot in sort of our 100A or equivalent courses. But we're going to talk about it now, which is why I want to go back and review where this sort of comes from, where you've seen it before, or at least seen something similar to it. So when we talk about covariance, you understand what it is. Other questions? Sorry, my phone was like vibrating in my pocket. I usually don't get like service in this little room I'm in. So it's weird. Other questions? So the takeaway from this is not, not supposed to be like an expert at covariance or correlation. Just the idea that of what a covariance is measuring. It's giving it unit values to the degree to which there's a trend for people to score above or below or on opposite sides of their means on two different variables. And then we can standardize that and make it into a correlation if we want to. And we will for, at least at first, and then we'll talk about covariance without the standardizing part. So any questions? Anything still confusing about this? If it is a little bit confusing, it's okay if you've seen it before, because I am explaining it in a different way than you're probably typically used to seeing it taught, and that's all right. So this should be adding to your understanding, not necessarily taking away. It's just a different way of looking at it, not like it's an alternative or better way. It's just a different way of thinking about it. So let's think about the future of the course, the next little bit. Why would talking about covariance be something that's related to, or something we should talk about when it comes to measurement theory, trying to develop tests? Where would covariance come in? Where would this idea of how people score, patterns of scoring on different variables come into measurement theory altogether? You're getting there. So if people with certain types of disorders are given different sort of measures, you would expect them to have similar types of responses, correct? Right? If they have the same disorder, there should be something similar about how they respond to different things. So that's getting at sort of internal consistency. If there's a bunch of items on the same test, the same measure, like if we create a 20-item test that measures depression, if depression really is driving their responses, like someone has depression and it's actually, driving how they respond to the items, you'd expect that someone who's all their items should be above. You should have a high covariance between multiple pairs of items where they should all be above the mean. People who are not should all be below the mean. There should be consistency across how they respond to scores if those items really are measuring the same phenomenon, right? Let's say, that was Jessica, I think, that was just talking. So let's say Jessica creates a depression inventory, and so do I. And I've had one that's been around forever. It's like the one that's been used forever, and people use that. And Jessica's trying to create one, and she wants to know if hers is as good or is measuring the same thing as the sort of standard measure. Well, if you gave people the two different measures, you would want to see that if people are above the mean on mine, they should also be above the mean on Jessica's. People are below the mean on mine, they should also be below the mean on Jessica's. There should be a sort of positive covariance between them. And to do that, to use that metric, that comparison, that's actually looking at validity, which we'll talk about later on. If the scale is valid, it should correlate positively with other scales measuring the same thing. So there's internal consistency, there's reliability. If this is the same test given twice, so you come in and take a depression inventory one time, like today, you come back multiple days from now and take the same test, you'd expect if you scored above the mean before, you should also score above the mean again. If you scored below the mean before, you score below the mean again to show that there's some consistency in scoring across time, and that measures reliability. All right, so all the things that we talk about, a lot in terms of testing, the test is reliable, it's valid. All these things are based on, in many ways, very simple ideas of how the responses covary across times, across people, across measures, all kinds of stuff, and how we use those measures actually determines whether we're talking about validity or reliability or some of the other things we'll talk about. But it's all using very basic sort of ideas that you've already learned, which is correlation. It's just, you got to think about it a little bit more. It's about trends. How do people respond on things, and are they actually staying relatively consistent? If it's about consistency, then we're talking about reliability. If it's about sort of the match between different measures, then we're talking about validity. So we'll talk about that more as time comes. But it's important to understand why covariance is the way it is and what it actually means and stuff. So when we talk about those things later on, it'll actually make sense of why we're using covariance and correlation in this way to measure reliability or validity or things like that. All right, we had enough of. Go for it. It could be either one. Yeah, it could actually be either one. You can actually covary things that are either items within the same test. You can take an entire test and compare that to another test. Like if you want to look at how much depression and anxiety, for instance, covary, you can apply it in any way you like. Anything that's measured and that the same person or same group of people respond to both, you can look at covariance for any of those things. But how you interpret the correlation or the covariance from what you're talking about will change whether you're talking about validity or reliability. It will depend on how you're sort of using it. Even if it's the same exact mathematical function, we're going to use it for different things. And it will make more sense as we go forward. But I just want to make sure that we had a good foundation on what's going on with covariance before we sort of moved on and talk about other stuff. Any other questions, or you want to move on? All right, I'll take your silence as let's move on. Give me a second. I brought this down. All right. Moving on. Okay. Talked about that. And this is sort of giving you an example of sort of applied to what we're talking about. Just sort of walk through sort of how it works for a second. And sort of fill out the first part of this. So what I want is, in this column is sort of x minus x bar. So if my x is 11, x bar is 5.952. So somebody tell me, what's 11 minus 5.952? All right, so 5, so I can write it in the right place, 5.048. That's why I want to point out sometimes it looks like I'm being weird. It's because what you're seeing in your screen, right? So this is what I see, except without the light board studio. So looking at the glass, I'm just looking out. I see nothing of the graphics. I can see this. I know this is here because I can see it. I have a monitor that's off screen that you see me looking at. I have a monitor in front too that shows me the graphics. Right, so I can see the graphics combined with me. This is just a camera shooting me through a glass window. This thing, right? Sometimes it gets tricky. So I lay the graphics on there. I can see it in the monitor, but I can't see it here. So I have to sort of figure out where my hand's supposed to go. Right, to sort of figure out how to line up, oh, okay, about here, and then sort of write it down. So sometimes it looks a little goofy because I'm trying to figure out, wait, where the hell do I put my hand to get in that little box? But anyway, so what about 26 minus 14.524? All right, 11.476, and then multiply those two together. $57.938. So I think I got 931. Okay, so look down this column here. What do you notice? When do you have values that are positive here, and when do you have values that are negative? By the way, pretty sure this is wrong, because when I deleted this score up here to make it blank, I think it recalculated this. So that's not good. Anyway, no, go. So yeah, tell me, when do you see? What do you notice about the positive scores and the negative scores? So I just want to point out that, like, this is just demonstrating the idea that, there we go. That should be the right number. Okay. I start written in the right place. Yeah. Okay, there we go. So I just want to make sure that the sum stayed correct there. Oh, this is right. Okay, so to reiterate, this is positive because both the cigarette consumption and coronary heart disease values are both above the means. So they're both positive. We multiplied. That's positive. Here, number 14. The cigarette consumption and coronary heart disease are both below the means, so they're both negative. But when we multiply across, they become positive. Now, you have some negatives. This country, number 13, they happen to be below the mean, right? So they're below the mean on, yeah. You can see my work. No, I'm not right. I'm just pointing. Do you see my hand pointing? Yeah, so I'm not writing anything. I'm just pointing. But I can write. If that helps. So if you look at number 13 here, right? Can you see that? You see the circle? Okay, good. Yeah, I was just pointing at stuff, but yeah, maybe I should just circle. So because that is below the mean, and you get a negative number here, right? But their score for coronary heart disease deaths is actually above the mean. So their two scores are on opposite sides of the mean, which is why you're getting a negative product here. But as I look, there's a general trend. Even though there are some negatives, there's a negative there, negative there. Most of the negatives are pretty small numbers. And it's usually because there are countries that generally are right around the averages, right? It's a little bit below, a little bit above. They're right around the averages. So they're sort of flip-flopping around. But generally, we're getting mostly positive numbers. So when we add them up, we're getting our sum of products is mostly is a positive number, a large positive number. So there's a general trend. Now, what if there was no trend? Sometimes, they're on both sides of the mean, sometimes they're on opposites, right? You'd have about an equal number of positives and negatives doing down here, right? And equal in size. It would just, be flip-flopping around negative, and this number would be near zero. All right, so covariance is near zero, tells you there's no general trend to which side of the mean the values tend to be on. Sometimes they're on the same side, sometimes they're on opposite sides. And, so you end up getting a number that's close to zero, and then when you go to standardize that, you get a correlation that's close to zero, or that is about zero. All right, so here we get a positive number, it's fairly large, so there is something here, there is a positive sum of product. So let's take that a step further and look at, here's, what do we do with the sum of products? Well, it's that top part of this thing, right? So the sum of products was, I already forgot the numbers, like 220 something. 222.524 is what this is. So 222.524, I believe. Over, there's 21 countries, so that makes this 20. 20 countries minus 1 is 19. Okay? Now, I admit, it's a little bit confusing because here we have two means, and yet we're only losing 1 degree of freedom. Now, that gets a little bit confusing, and it's because of the correspondence between this and variance, because variance is just one variable, therefore you just lose 1 degree of freedom. To make that correspond, they just left the 1 degree of freedom here, because you really have 20 pairs of products minus 1, but it's a little bit misleading because there are two means. You think it should lose 2 degrees of freedom, but it doesn't. So if I divide those, what do I get? 222.524 divided by 20 equals what? 11.126, go with 3 decimals, sounds about right. So what does that mean? It's something weird like 11.126 deaths per cigarette or something like that, because it's a combined sort of metric. It's in both of these metrics together. So it's like 11.126 deaths per cigarette or something like that. Okay. It's very hard to interpret covariance. Is 11.126, is that a large covariance? Is it small? We really don't have an idea of what this is in terms of size, which is why we tend to standardize it into correlation. What do we know here, though? What does this value tell me about the covariance between these variables? Sure. No, so we're step 1 towards a correlation. We haven't got the correlation yet. So we took we converted variance over to this idea of covariance, and so we just applied this equation here to this set of data. We took 11 minus 5.925, which gave us 5.048. We took 26 minus 14.524 and got 11.467, multiplied them and got this product. And then the rest of them were sort of done for us to get a sum of products, which is the top part of this equation here. This is the sum of products over degrees of freedom again. All right, so down here, this value down at the bottom, this is our sum of product. Is the 222.524. That's the top part. So then the next part of that was to then divide it by degrees of freedom to get our covariance, which is 11.126. So we haven't got the correlation yet. So it's not, we didn't convert a correlation into covariance. We calculated the covariance, and now we're going to convert that in the next slide to correlation. So this is basically like an unstandardized correlation. Yeah, go ahead. Yeah, and it's for all countries. It's this is the covariance between cigarette consumption and coronary heart disease for all 21 countries. Like it's basically the average relationship between cigarette consumption and coronary heart disease for these 21 countries. You could. It wouldn't be a super reliable thing with just 2 points. It's like sort of trying to calculate a variance with just 2 points. But you could. Just wouldn't be. It would fluctuate quite a bit. But for the most part, we're going to compute the degree of relationship between these 2 variables across these 21 countries to get an idea of sort of how much they relate, and then we can look at, well, all right, well, what does that mean for each country? We'll talk about that in a second. We go to like prediction. We can sort of see, all right, well, we predict that they'd have this much coronary heart disease, but in fact, they have more or less. We can actually look at residuals and things. So we can actually apply it to each particular country, but we need all the countries together to sort of get the idea of how much these things actually relate. And they relate by a covariance of 11.126, which is hard to interpret, except the main thing we know from this is at least it is positive. There's a positive relationship between cigarette consumption and coronary heart disease. So as cigarette consumption goes up, we know that coronary heart disease goes up. And it goes down, so does coronary heart disease. We know there's a positive relationship somehow, but it's hard for us to gauge if this means that there's a strong relationship between cigarette consumption and coronary heart disease because it's unstandardized. It's in its own weird death per cigarette sort of metric. So what do? We're going to convert it over to something more standard so we can actually figure out if this is a large or a small relationship. So let's look at that next, which is where the sort of the correlation comes in, and why you hear a lot more about correlation than you do covariance, because it's a lot easier to interpret, a lot easier to sort of figure out. But we're going to learn some new tricks about how to make covariance useful for us we need the actual metric, the variance in there to actually use it for some of the measurement things we're going to talk about. All right, so if a correlation is just the standardized covariance, so we can then figure this out. Actually, it's on the next page. So it's covariance divided by the product of those two standard deviations. So if my covariance is this 11.126, all right, so I can put that here, 11.126, and my two standard deviations, those are supposed to be subscripts. I don't know why they came big like that. It's weird. 2.334 times 6.690. Oops, did it wrong again. 6.690. So what do I get if I take 2.334 times 6.690? What's the product of those two? Looks like, okay, so 15.6, well, this is one of those ones where like, all right, the 6 makes the 4 5, and the 5 makes the 4 another 5. That depends on how far you go back. So 15.614. And on top you get 11.126. Didn't help well. If I divide those, 0.126 divided by 15.614, I get 0.713. Now, this is something we're much more comfortable with. A correlation of 0.713, what does that tell you? Yeah, it's not perfectly related because that would be 1, but we're creeping up towards pretty strong. I mean, 0.713 is a pretty strong relationship, correlation-wise, and it's positive. So this now tells us, just how strongly those two variables are related by taking it and putting it into a scale that we're sort of used to, where we can tell what is large and small in terms of correlation. This becomes a lot easier to interpret than just looking at the 11.126. But the direction of the relationship and how much they're related was actually built into the covariance. All we did for correlation is just standardize it so that it's easier to sort of interpret. All right? So far, so good? Yeah, I didn't really explain it so well, except that if you were to look at this, right, forget about, actually I can't cover it, but if you're, looking at the top, you would expect that you would lose 1 for x and 1 for y. That makes sense, right? And that will come back around in a second to make it even more confusing. But we typically divide by n minus 1. The reason, at least as far as I can tell, actually I don't know this for a fact, but as far as I can tell, the reason is, if you look at the measure for variance, right? So remember, covariance is just the variance shared between two variables. So they correspond, where variance is x minus x bar squared over n minus 1. If we spread those out, so it's x minus x bar and x minus x bar again, it's still divided by n minus 1 because we're still talking about the same x. So when you replace 1 with y, put the y there and a y bar there, right? It still stays n minus 1 just to keep it sort of parallel to variance. So the covariance between the two of them, even though there's two variables here, we're still dividing by n minus 1 and not n minus 2. At least as far as I can tell, is to sort of keep this parallel with this, even though it's going to get more confusing because when we actually go to figure out a significant value for the correlation, we're going to look it up with n minus 2. So this makes even less sense. All right. But I think it's just to keep. I imagine there's probably some simulation data to show this too, that the covariance, just like variance, is closer to the actual population covariance when dividing by n minus 1, not 2, not n. So there's probably some other reason there too, but just think about it as, let's keep the covariance parallel to variance, which means we got to keep it divided by the same number. It's not a perfectly good explanation, but at least it's something. All right, so we plug this in, we get correlations of 0.713. All right, so sign's positive, which means there's a general low left to high right, so the trend. If it were negative, it would mean we going high left to low right. But even if this were negative 0.713, it wouldn't change the degree of relationship. That's what it says. Would not alter the degree of relationship, just the trend, the direction. Right, so a 0.713 and a negative 0.713 are equally as large. They're the same size correlation, just in opposite directions. So a lot of times people will get confused and think that because it's negative, it's less or something. It's not. It has nothing to do with the degree of relationship. It's just the negative versus positive is really more to do with it has all to do with just the direction. All right, so now you have a correlation. Now what? So in terms of magnitude, 0.713 seems like a big one. So we're like, okay, that's a pretty decent correlation. But small correlations in large samples can be seen as big. And large correlations in very small samples, like ours, only 21 countries, aren't always considered that large. So it depends on a couple of things. The magnitude of the correlation, obviously, but also the size of the sample. Sample size has a lot to do with sort of us deciding whether or not a correlation is significant, meaning that it's significantly different than zero. Like, do we have a correlation that really is something that exists? There is a relationship. We usually compare that to zero. So you can actually do, test for R, do a significance testing for R, where you have a population parameter rho that we're going to test against. We're assuming rho is zero under the null hypothesis. Hopefully you remember null versus alternative hypothesis testing and stuff. So we're setting up this null hypothesis where the correlation is zero, right? So under the null, we believe that, there's no correlation. It's just there's no relationship between variables. We take a correlation then and we compare it against that assumption of no relationship to see if our correlation differs significantly or substantially from zero. And we're actually way past time. It's 3:11. Doesn't the class end at 3:05? Or am I spacing that? All right. So I don't know, the fact you didn't say anything means that you were just so enthralled with the material that you just don't want to keep going. I don't know. You find it so interesting you got to keep going. So I will, on occasion, just keep going. So if you see that it's getting close to time, give me a heads up or something, because I will just keep going. I get into this stuff, thinking about things, and I'll completely lose track of what time it is and stuff. So let's stop here. We'll come back and talk about some testing of this stuff, a little bit on how this relates to regression, which is really short, and then we'll start classical test theory and all that stuff on Thursday, and sort of I think bring us back to being more sort of on track. Any immediate questions you have or anything right now, let me know. If not, I'll close this down. I can stay on Zoom for a little bit if you have individual questions, like sort of office hours. Otherwise, I'm going to end the lecture here. So it's over time anyway. So I can stop the recording.